Hey guys, what's going on? It's me, Mr. V. Today I will be teaching you about density. Let's get started. Here is a great story, or as some would call it, a tale, told by Vitruvius, a Roman author, architect, and civil engineer. The tale he tells occurred in ancient Greece over 2,000 years ago, and this tale revolves around a beautiful gold crown. King Hero II of Syracuse decided that he wanted a new crown created to honor the gods. So King Hero gathers some of his finest gold and summons a goldsmith to create for him a crown worthy of the gods. The goldsmith takes the gold and returns later with this beautiful crown. However, King Hero, after receiving the crown, feels uncertain that this crown is truly 100% gold. He believes that the goldsmith may have swindled him and may have kept some of the gold for himself, and in turn replace that gold with a less valuable metal like silver. So the king is incredibly suspicious and calls on Archimedes. Archimedes, a Greek mathematician, engineer, inventor, and astronomer, was known at the time as a great problem solver, and he began to think about how he would test whether this crown was in fact made with all of the gold provided by the king. However, the king gave very specific directions that this crown could not be destroyed or altered in any way. So Archimedes was thinking about this one evening as he drew up a bath, and he realized when he sat in the bath that the water level rose, and as a result, some of the water poured out of the tub. As he thought about this, it occurred to him that the water level that he displaced was equal to the amount of space that he took up in the tub. Excited about his new discovery, he yelled, "Eureka!" He was so excited he hopped out of the tub and ran through the town naked, yelling "Eureka!" which means "I found it." What Archimedes found was that he could use the principle of density. And since he couldn't melt down the crown into a shape that would give him something geometric and would be easy to measure the volume and the mass and compare it to gold, he used this water displacement method to find the volume of the crown. And as you will learn, density is a measure of how much mass you have in a given space. So now that he's been able to determine how much space this crown takes without altering or destroying the crown in any way, and finding the mass of it and comparing this outcome to real gold, he was able to determine and report to the king that this crown was in fact not 100% gold. Now many would say this story is fictitious or just a tale to illustrate this principle. However, you could see that despite that, it still tells us the great benefit to the understanding of science and density. So now, whenever we use water displacement as a method to find the volume of objects, we have Archimedes to thank. Because of this, it is known as Archimedes' principle. Before we begin talking about today's topic, let's review some important vocabulary terms. The first term is mass, and as you know, mass is a measure of the amount of matter, or how much stuff you have. Think of it as how many particles make up everything around us. Remember that when measuring mass, we would be using an electronic balance. When we measure, the quantity we obtain would be with the unit of grams. And here you see the electronic balance we will often use in the lab. Another important term to review is volume. As you know, volume is the amount of space that's taken up by matter or by the stuff we have. The space taken up by the particles that make up all the matter around us. Now, you have learned in geometry that when measuring the volume of geometric shapes, you would use a ruler and given formulas to calculate their volume in cubic centimeters. Now, in chemistry, we're not so lucky. We don't usually get perfectly shaped objects. We often work with irregular shapes, and to measure their volume, we are going to use the water displacement method. Using a graduated cylinder, filling it up to a certain level, you could then place that object in there and see how much water rose. The difference between these two values is going to tell you the volume of the object in the water. This will be measured in milliliters. So now that brings us to the topic at hand, and that is density. Density is a measure of the amount of mass per unit volume, or how much stuff you have in a given space. Now, as you can see, chemists love density, and the density formula does involve a heart, but it's a little sadder than that. You can kind of see it as a broken heart. Well, if you look at the sad face, or D equals, you can see it kind of resembles a heart split in half. The top half representing the variable on the top, and that's mass, and the bottom half resembling the variable on the bottom, which is volume. So whenever we calculate density, we are going to take the mass, which of course we measure with the electronic balance, and divide it by the volume, which we know in chemistry we often measure with the graduated cylinder. The unit, of course, will be a unit of mass, usually grams, over volume, milliliters, or possibly cubic centimeters. Now, while the formula for density is pretty easy to memorize, do not worry, you will not have to have it memorized, and this is often seen on your reference material. Here you can see it's the first formula under the other formulas category. Again, density equals mass divided by volume, or D equals m over v. Now, the property of density has us ask the question, how much does it weigh when a material fills a certain amount of space? Here's an example of that question. Let's consider the following objects and ask ourselves, how do these masses compare? Well, let's assume that these three cubes all have the same volume, therefore they all occupy the same amount of space. However, because you can see we have styrofoam, wood, and then steel, we know that their masses are going to be a little different. The styrofoam, when weighed, would be incredibly light, the wood would be somewhere in the middle, and of course that steel would be very heavy. So even though their volumes are all identical, we can see that their masses are incredibly different. The reason is the styrofoam, the particles are not as tightly packed or as dense, so there's not as much matter for that amount of volume. The wood, of course, will have a few more particles, but the steel has particles that are tightly packed together, giving us a very dense material, and even though it has the same volume, or takes up the same amount of space as the other two cubes, because the mass is so great, the density will also be far greater. Another question we could ask ourselves that applies to this is, how do the volumes of the following compare? Well, let's say you have a pound of feathers and a pound of bricks. The question is, which is heavier? Well, hopefully you said that they're the same weight, because a pound is a pound no matter what. So a pound of feathers, though, what would it require to have that? You could probably imagine a giant pile of feathers just to make up a pound. However, when it comes to a brick, to have a pound, you'd really only need one brick or maybe even a fraction of a brick. So even though their masses are the same, their volumes are incredibly different. The reason is, again, the feathers are not very dense. They don't have a lot of particles in a small amount of space, so they take up so much space to create that one mass. The bricks, on the other hand, their particles are so compact and so crowded that you really have so much matter in a much smaller area, making the brick much more dense. Here's a favorite experiment done by chemists always when involving density, and this is the density column. And you can see what has been done is they've taken different substances that are immiscible or won't mix together, and they've layered them based on their density. So as we've seen, objects that are more dense, like the steel block or the brick, are going to be heavier because their particles are more compact in that small amount of space, so they're going to sink to the bottom, while objects that are less dense will rise to the top. So let's ask ourselves some following questions. Which of these substances is the most dense? Well, if you look straight to the bottom, you're correct. There we have honey as the most dense substance. The second question we want to ask is, what is more dense than water? Well, you can see the water is right in the middle, and it has been given a green food coloring to just kind of give it a different appearance. And we can see that there are actually 3 substances that are more dense than water. And again, more dense means they're going to sink to the bottom. So those 3 substances are the Dawn liquid soap, the Karo syrup, and of course that honey. But then whenever we ask ourselves the question which is less dense than rubbing alcohol, you can see rubbing alcohol, only second from the top, is only going to be more dense than one substance, and that's the lamp oil. Alright, let's take a look at some mathematical examples of density. Here we have an object with a mass of 50 grams and a volume of 10 milliliters. So we are asked to find the unknown of density. Well, using the formula, we know that density is equal to mass divided by volume. So this is really straightforward. We simply substitute our values of mass of 50 divided by a volume of 10. And when you plug that in, you get a density of 5.00 grams per milliliter. In the second example, we see that we have an object with a volume of 8.25 cubic centimeters. This object's density is 13.6 grams per cubic centimeter. Find its mass. Well, again, we're going to use the same formula of density equals mass divided by volume. And you're always going to substitute in the known variables. We know D for density is 13.6. However, we don't know the numerator M, but we can place the variable M over our volume of 8.25. Now we're going to need a little bit of algebra. It's not as straightforward as the last example. However, what you can see is we do need to isolate the M, which is find where it's at in the numerator, so we simply multiply both sides by 8.25, which essentially moves 8.25 to the other side and multiplies those values. So we end up with the value for mass of 112 grams. In this third example, we have a liquid which has a density of 0.87 grams per milliliter. The question is what volume or how much space is occupied by this liquid if it has a mass of 25 grams. So here our unknown variable is volume. And if we look at the density formula, which is density is equal to mass over volume, you will see that it's a little bit different than the rest. When we substitute our density and our mass in, we have 0.87 is equal to 25 divided by V. Now our unknown variable V is located in the denominator. Now this is the type of question that gives most students some difficulty. And the reason is we're solving for V and we're trying to isolate the V. However, to do so, you don't want it left on the bottom. So we're going to have to bring V to the top, and to do so, we multiply both sides by V. It's kind of like moving the V across to the other side. And what we end up with now is V times 0.87 equals 25. Now we can safely isolate the V now that it is on the top, because after all, we want to solve for a V, not 1 over V. And as you can see from here, we simply divide both sides by 0.87, so V is equal to 25 divided by 0.87. So be very careful when working on a problem like this. Now whenever we divide, we end up with a volume of 29 milliliters. Overall, density is one of the most important tools or ideas that scientists and chemists use, so hopefully you enjoyed watching this video and learned a lot. Moving forward, be sure you know exactly how to measure mass and volume and understand that the ratio of how much stuff you have in a given space is this principle of density. Thank you for watching. I'll see you next time. Size by volume. Melina, get out of here. Go. I need every... No, go. Go.